Welcome. This is our third and final lesson in Unit 1, and today we will look at Section 1.1 from the book, Linear Equations. We will hit all three objectives this time. Solve a linear equation, solve equations that lead to linear equations, and solve problems that can be modeled by linear equations. So, to begin, I want to talk about the idea of solution sets. So equations have solution sets. That is the set of all solutions. So for example, what is the set of all solutions to x squared equals 9? And maybe you realize there are two solutions, -3 and +3. So the set of all solutions is the set containing -3 and +3. What is the set of all solutions to x plus 3 equals 20? Well, there's only one solution. It's 17. The only number that works is 17. So this set contains only one element, the element 17. What is the set of all solutions to x plus 3 equals x? And this is a weird thing to ask, right? Do you see why this is strange? It's like saying you start with a number and you add 3 and you get back the number you started off with. Is there any number that you add 3 to it and you get itself? No, there is no such number. And so the solution set is empty. This is the empty set. This equation has no solutions. How about this? What is the set of all solutions to x equals x? Well, any number works. 10 equals 10, pi equals pi, -8 equals -8. So in fact, any real number is a solution. The solution set for that equation is all real numbers. So solutions can have a few solutions, one solution, no solutions, or infinitely many solutions. All those possibilities are there. Oh, and by the way, everything I've presented so far is called an equation in one variable, and that's what we'll really focus on. The only variable in all of these equations was just x. You might later find other equations that have x's and y's and z's all mixed together, but for us, we're going to focus on equations with only one variable. Now, a number in the solution set is said to satisfy the equation. So for example, 17 satisfies the equation x plus 3 equals 20. -3 satisfies the equation x squared equals 9. Here's another example. The number 17 satisfies the equation x minus 7 divided by 2 equals 5. And can you confirm that if you plug in 17? 10 over 2. Yep. So 17 satisfies that equation. One more quick definition. Two equations are called equivalent if they have the same solution set. So in fact, I drew two equivalent equations here. This equation, x minus 7 divided by 2 equals 5, is equivalent to the equation x plus 3 equals 20, because both of them have the same solution set, namely the set containing the number 17. All right, let's look at solving some equations. Now the key idea is to create equivalent equations that are simpler. I want to simplify and eventually just get x so it's all by itself on one side of the equal sign. So I have two expressions. I have an expression on the left side, 3x plus 4, and an expression on the right, 22. So anything I do to one, if I do the same on the other side, that equality will be maintained. So if I subtract 4 from both sides, -4, -4, I end up with the expression on the left, 3x, and an expression on the right, 18, and those continue to be equivalent. So I've just created an equivalent equation that is supposedly simpler. In fact, it is a little bit simpler because previously I had two constants and now I have only one. Well, what do I want to do next? How about divide both sides by 3? So I'll divide by 3, divide by 3. 3's cancel on the left, so x equals 18 divided by 3 is 6. And there we go. Usually I stop at this point and I say, there's my solution, x equals 6. If you really want to, you could also say the solution set is the set containing the single number 6. All right, a couple more equations to solve. X squared plus 2x equals x squared plus 10. Well, I see that I have an x squared on both sides, so let's subtract that out. Minus x squared minus x squared. And on the left side, all I'm left with is 2x. And on the right side, all I'm left with is 10. So now I can divide both sides by 2. And I end up with x equals 5. How about the equation on the right? Can you do that before I do? If you maybe pause the video for a second and see what you get. Let's see. The first thing I'll do is distribute the x. So when I distribute my x across this addition, I get x cubed plus x equals x cubed plus 45. Oh, and now I see I have an x cubed on both sides. I'll subtract that, x cubed, subtract x cubed. And on the left side, it looks like I end up with just x. And on the right side, 45. Ah, very easy. So there I've solved both of these equations. Now, I haven't actually said what a linear equation is yet, and in fact that's the name of this whole section, linear equations, so I ought to do this. A linear equation in one variable is an equation equivalent in form to ax equals b, where a and b are numbers and a is not 0. So take a look at this first example. Was that equivalent to something of the form ax equals b? I actually found it right here, 2x equals 10. That was one of the steps. So since my original equation was equivalent to 2x equals 10, then this equation is a linear equation in one variable. Similarly over here, my second example ended up with the expression x equals 45. Well, in fact, that is a linear expression as well. This is like my ax equals b, where the a part is actually just equal to 1. We'll spend the next few slides looking at tips and tricks for solving these linear equations. So that's what these next 3 sections here, if you look at the menu on the left, we will see tricks like combining like terms, clearing denominators, and expanding first. So let's take a look at those. Combining like terms. So sometimes you'll end up with a big mess, and the first thing you want to do is, well, you probably, even before combining, is distribute. Do all the distribution you can, and then look for like terms. Okay, let me expand this 2 out. So we get 3x plus 2x plus 8 plus 1 equals 6x plus 5 minus 7. Now, what do I mean by like terms? Those are terms that are just a multiple of x, so something like 3x or 2x and 6x. Those are all like terms. I'd like to combine them somehow. At least I'll begin with like terms that are on the same side of the equal sign. So the 2x and the 3x I can combine. 2 plus 3 is 5, so that becomes 5x. Also constants, the plus 8 and the plus 1, those are like terms. So plus 8 plus 1 gives me plus 9. On the right side, I can't combine 6x with anything else at this point, so it stays 6x. But I do have a plus 5 and a minus 7. Plus 5 minus 7 is minus 2. Okay, I've combined the 2 different sides individually as much as I can. Now I need to combine like terms across the equals. So I have a 5x and a 6x. How about if I subtract 5x from both sides? That way my x will end up being positive on the right. So get rid of the little squiggle there. Do minus 5x minus 5x. That way the 5x disappears from the left. All I have is 9 remaining. On the right, 6x minus 5x is just 1x, and a minus 2 remains. Now it's pretty straightforward. I can add 2 to both sides, and I end up 11 equals x. So x ended up on the right side of my equation, but that's fine. It looks good. I found my solution, x equals 11. So as you're solving equations, look for ways that you can combine your like terms as much as possible. The next idea is clearing denominators. So with this, sometimes you have fractions. You want to find the least common multiple of all the denominators. So I have a 2 and a 6. I have 2 different denominators in this problem. What is the least common multiple of 2 and 6? And, oh, it's just 6 itself. 6 is a multiple of 2. So now that I know that 6 is the least common multiple, I'm going to multiply both sides of this equation by 6. So on the left we get 6. Now I'm going to distribute my 6, and on the left side 6 times x plus 3 all over 2 plus 6 times x plus 1 all over 6 equals 30. And I have some factors I can cancel, or at least reduce. I have a 6 over 2, and let's see, they both have a factor of 2, so that's like a 3 and a 1. So that's how that simplifies. And the 6 over 6, those are both the same, so that just cancels as 1 and 1. So my denominator on the left is just 1, so this whole thing becomes 3 times x plus 3 plus x plus 1 equals 30. Distribute the 3. 3x plus 9 plus x plus 1 equals 30. Combine like terms, so the 3x and the plus x, that's going to combine to give me 4x. The 9 and the 1 combine to give me 10. Let's subtract 10 from both sides. Looks like 4x equals 20, at which point we get, let's see, I'll divide both sides by 4. Divide by 4, divide by 4, x equals 5. And there's our solution to this equation. Let's do another example with clearing denominators. What if our variable x is in the denominator? How do I handle that? Well, same as before, I still want to find the least common multiple of all the denominators. In this case, 4 and x and 8. 4x and 8. Well, the least common multiple of 4 and 8 is just 8. So I need to find the least common multiple of x and 8. And I can always just multiply things if I don't know any better. So 8x is going to be our candidate for the least common multiple. Right. So I'm going to multiply both sides by 8x. 8x. This thing times 8x. So on the left, when I distribute, I get 8x divided by 4 plus 8x times 9 divided by x. And on the right side, 5 times 8x all over 8. Now let's look for common factors on the top and the bottom of these fractions where I can cancel. So I have an 8 and a 4. 8 divided by 4 is 2, so that gives me a 2 and a 1. Oh, this is nice. This guy in the middle, I have a factor of x on the top and a factor of x on the bottom, so those cancel away. And on the right, factor of 8, those cancel each other. So after reducing, this looks like 2x plus, let's see, 8 times 9 is 72 equals, and 5x remains on the right. Don't forget there's a little x right over there. All right, let's combine our x's together. I could make all my x's on the left, in which case I'd have to move my number over to the right. So let's just move my x's to the right. I'll subtract 2x from both sides. And I get 72 equals 3x. Pull out your calculator, do a division, divide both sides by 3, and we get 24 equals x. There's our solution. Let's move on to the last technique for solving linear equations, expanding. All right, so when you have things multiplied together, it can be really difficult to get at the x. Ultimately, we want to get the x by itself on one side of the equation, and the very first thing we have to do is just expand everything. So I'll use the distributive property. I'll distribute x plus 9 across my x minus 1. I get x plus 9 times x minus x plus 9. I'll just leave that in parentheses, times 1. And that equals, this x plus 3 squared, let me write that, x plus 3 times x plus 3. And when I distribute x plus 3 across, I get x plus 3 times x plus x plus 3 times 3. All right, and another distribution here. We end up x squared plus 9x. Oh, here's a nice case of distributing your minus. Be very careful. Minus x minus 9 equals x squared plus 3x plus 3x plus 9. Okay, everything has been expanded. Let's combine like terms. So on the left, I see a 9x and a minus x squared. So that becomes plus 8x. And on the right side, I have a plus 3x and a plus 3x, so x squared plus 6x plus 9. Okay, now let's start combining like terms on the two different sides. How about the squared? Oh, there's a x squared on the left and x squared on the right. I'll subtract that from both sides, minus x squared, and we end up with 8x minus 9 equals 6x plus 9. Now let's combine my x terms, the 8x and the 6x, so I'll subtract 6x from both sides, minus 6x minus 6x, and I end up with 2x minus 9 equals 9. All right, I have my constants. I have a minus 9 on the left and a positive 9 on the right. Let's move all my constants to the right, so I'll add 9 to both sides. Plus 9, plus 9. Maybe we'll move up a little bit to continue here. So I end up with 2x on the left, and I end up with 18 on the right. And as my last step, in order to get x by itself, I'll divide both sides by 2 and end up with x equals 9. All right, it took a little bit of work, but there we go. We got it. X equals 9. There's our solution. Sometimes problems ask us not to solve just for x with a bunch of numbers around, but to solve for some particular variable. Consider this expression, a equals hw cubed over 6r. So maybe this is some formula for some special use, but we want to solve for h. What that means is, if I solve for something, it means I want to get that variable by itself on one side of the equation. So just as I look at this, I'm thinking h times w cubed all divided by 6r equals a. What do I need to do to isolate that h? Well, the first thing is probably get rid of that denominator. So let's multiply both sides by 6r. So times 6r times 6r, and that's going to make the 6r cancel on the left. h w cubed equals a 6r, or 6ar probably. And now to get h by itself, I just need to divide by that w cubed. Divide by w cubed. On the left, those factors cancel. And now I have h all by itself. And like I said, traditionally the number goes out front. So I'll call that 6ar all divided by w cubed. So this is something else we might do in solving equations. Take some formula, some expression with a bunch of variables, and solve for some particular variable. Okay, our last topic in this section is a word problem. So sometimes you come across word problems where you need to solve a linear equation to get the solution. In this word problem, the perimeter of a rectangular window is 36 feet. This is a very large window. The width of the window is 4 feet more than the length. Now to me, width and length sound kind of similar, but they say the width is longer. The width is 4 feet more than the length. So since the width is the longer part, let's label this picture on the bottom with width. And on the side, the shorter side, that's length. The width is 4 feet more than the length. What are the dimensions of the window? All right, so it always helps to put some variables in here. So maybe length, you can call this L. Now in math, when we use L as a variable, we'll make it a cursive, a script L. Width could be W. But maybe let's work in terms of L. I only need one variable. In fact, I'd only want to use one variable. Instead of calling that width W, let's call it L plus 4. Now, both dimensions are determined with just one variable. I haven't used the fact yet that the perimeter is 36 feet. How do we get that? Well, let's look at the perimeter, all four sides. This top side is going to have width L plus 4, and the right side is going to have length L. And so when I add all of those together, let's see, I have two L's going across, so 2 times L, and this L plus 4, I have two of those for the top and the bottom, so 2 times L plus 4. That's my perimeter, and so that is 36 feet. Ah, look at this. So now I have the equation that I need to solve. I've set up a linear equation. All right, let's work it out. So 2L plus, distribute the 2, 2L plus 8 equals 36. Let's combine like terms. I have a 2L and a 2L, so that becomes 4L plus 8 equals 36. Let's combine the like terms of our constants. We'll put them on the other side, so on the right-hand side. So by subtracting 8 from both sides, that gives me 4L equals 28. Now I can divide both sides by 4, and that leaves me L equals 7. So we figured it out. The length of this window, the short side, is 7. So what does that mean for the long side? Because the problem asked what are the dimensions. It wanted to know both of the dimensions. So the width, 7 plus 4, is 11. So yeah, this is a very big window. All right, so there it is. Those are some linear equations, thinking about solution sets, some techniques for solving equations, solving for a particular variable, and looking for word problems where you might need to solve a linear equation in order to solve the word problem.